is a simple MNIST problem. Okay. Now, fortunately, TensorFlow has the input data in the form of MNIST for us already, so we don't need to load the data from anywhere. Okay. Importing the TensorFlow library will be more than enough to get us started. Okay. So we're going to import TensorFlow, and then from the examples of TensorFlow, we're going to import the MNIST dataset as well. We're going to load that data. Let's check that out. So parallelly, I'm executing. So you might want to have a look out over here. Okay, just refresh that. So I have the MNIST dataset with me, and see how the moment I execute some code using data.read datasets, it extracts all the MNIST data that is already there inside TensorFlow, and it loads it up in the memory for us. Okay. Now, X is a placeholder for the 28 by 28 image data. So like I said, each of these images will be a 28 by 28 grayscale image. So basically they will have 784 pixels. Each of these images will have 28 into 28 pixels. Okay. So we define a placeholder for that, for each of these pixels. And keep in mind, we do it like this. We do it 28 by 28 equals 784 here. Okay. So this goes to show that we may need to reshape our data somewhat. Okay. Done. X is defined. Now Y, here is the placeholder for the correct answers. So let's say if you're going to look at an image which says 3, I want Y underscore this variable to be 3. So this is basically a placeholder for all our right answers for the Y, the variable that we are trying to predict. Okay. Now look at this and tell me what we are trying to do. The W, or the weights, is a TF dot variable, which is, in this case, we are initializing all of them with zeros. All the weights, we are initializing them as zeros. And the shape here is 784, comma 10. So what does this mean? This is how we are going to construct our neural network. Okay. We are going to have these inputs, and this will be pixel 1, pixel 2, pixel 3, all the way till pixel number 784. So our input layer will consist of 784 values for pixels. Okay. And then in the output layer, we are going to have 10 neurons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We are going to have 10 neurons, and each of these neurons will be the probability of class. What do I mean by that? So this neuron will be probability of digit 0. This will be probability of digit 1. This will be probability of digit 2. This will be probability of digit 3. And finally, probability of digit 9. So each of these neurons will give me an output probability. And by seeing these probabilities, let's say for a particular image that goes in here, we get this 0.8, 0.1, 0.01, 0.08, and then finally here we get something like 0.01 or something. Okay. So all of these probabilities will add to 1. Okay. All of these probabilities will sum up to 1, and whichever has the highest probability, let's say in this case it is here, I'm going to take that as my prediction. So I'm going to feed an image inside this neural network, get 10 probabilities, select the neuron with the highest probability, and then output that as my prediction. So this will be neuron 0, neuron 1, neuron 2, neuron 3, neuron 4, and all the way till neuron 9. So let's say if neuron 4 has the highest probability, that is going to be my prediction here. Okay. So now With this architecture very clear, think of how many weights that we are going to need. So for each neuron, the input needs to go through, right? For each neuron, I have 784 inputs. For this neuron, I have 784 inputs. For this neuron, I have 784 inputs, and so on. Okay? Now, each of these neurons will have one bias. This neuron will have its own bias, 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 and so on. So each neuron has a bias and 784 inputs. So I have a total of 784 into 10 plus 10. These many weights that I have to train on a very simple neural network. So I basically have 7,850 weights that I have to train. Okay. So that's why the weight matrix is actually a 784 by 10 matrix, and the bias is actually a vector of 10 values. Okay, so we'll need one bias for each neuron, and we'll need 784 inputs for each neuron. Hence, the dimensions of these vectors and matrices are like this. So the dimensions for the weight matrix is 784 by 10. The dimensions for the biased vector is 10. Okay. Now finally, I'm going to put it through a softmax function. Now the difference between a sigmoid and a softmax function is very simple. Let's say I have two neurons here and some input that is going inside this and an output that comes out. Now what sigmoid will do is give out probabilities. Now let's say it will say that this probability is 0.8 and this probability is 0.6. Okay. What a softmax would do is give me probabilities that add up to 1. So if this is going to be 0.7, this has to be 0.3. These guys don't add up to 1. But softmax adds up to 1, which is exactly what I want, right? So I want the probability, given an image, I want the probability of each of these digits, and I want them to sum up to 1. And hence, in an output, as an activation function, I'm using softmax and not a sigmoid in this case. Okay, but you can use sigmoid. There's nothing to stop you from choosing sigmoid as the activation function. So look at how this computation now looks like. I'm going to matrix multiply x and w, that is the input and the weights. I'm going to add the bias, and then finally I'm going to put it through a softmax function. The whole deal, I'm just putting it through a softmax function, and I will get 10 probabilities in return. Okay, so that's our neuron. Now cross entropy, like I said, is defined, has a predefined implementation in TensorFlow so that we can measure our errors or measure our losses. I strongly encourage you to look into what a cross entropy is and try playing around with more of these loss functions in TensorFlow. Okay, so fortunately TensorFlow has a very easy implementation of cross entropy, and we are going to just go ahead and use that. As always, we'll use our gradient descent optimizer and try to minimize this cross entropy function. Okay, so given this function, can we minimize it? I'm going to initialize my global variables, start the TensorFlow session as always, run the TensorFlow session so that the variables are initialized, and now we are going to perform 1,000 training steps. Since we are training 7,850 weights, we will need some iterations. And in this case, we are using 1,000 iterations so that our network is trained well. Okay. Now, for those people out there who do not have a very decent computer with not very decent RAM, what I've done is I've batched the data. What do I mean by batching the data? So at every iteration, 100 images will get fed into the system, and then the training will happen. So the training will not happen on all 55,000 images, but it will happen 100 at a time. Okay. So I finally run my session, and then I do my predictions. Okay. So once those predictions are done, this is what I'm going to go through. So what this means is these are my predictions. So this y is the prediction. So if I just were to come back quickly here, this y is basically my prediction. This y underscore is basically my ground truth or the true values that is present in the data. And I'm going to equate them, which will give me some accuracy score, which I'm going to sum up or average it out so that I can see how my accuracy is. And then finally, I am going to print my accuracy. Okay. So what we did here is we have 784 pixel inputs. We have 10 neurons that we have initialized. Each of these neurons will take in the input, multiply it with the weights, sum it up, add the bias, put it through a softmax activation function, and out comes a number. There will be 10 such numbers that will be coming out, and each of these numbers will be the probability of being a particular digit. Okay, so with that, I'll just give the whole script a run for completeness, and then we will check out how our test accuracy plays out. Okay, so I'm going to press F5 here, and I want you to focus on this. So it is extracting the MNIST dataset right now, and with lightning speed, it actually initialized all those 7,850 weights, went through 1,000 iterations of the gradient descent optimization, and then finally spat out a test accuracy of 90.76%, which is really good, keeping in mind the fact that we have only designed a simple neural network. So in the next session, when we will design our deep neural network, we will push this accuracy scores beyond the 95% block. Okay. The reason why we are using neural networks in the first place is to get legendary accuracy scores, right? Although it is kind of difficult to get them right, once you get them right, you really have a very sophisticated algorithm at your disposal.